So when we run a chemical reaction, as a chemist, we usually want to know three things about that reaction. Okay. The first thing you learned how to do, hopefully, in Chem 101. So the first thing we usually want to know about a chemical reaction, that's supposed to be a check mark. First thing we want to know about a chemical reaction are what are the reactants and what are the products? And that's important because if we know the reactants and the products of a chemical reaction, we can then balance it, and then if we can balance the reaction, then we can do stoichiometry with it, right? And that's all Chem 101 stuff, right? And this is what allows me to say, hey, if I want to make 15 grams of this product using that reaction, how many grams of each reactant do I need to put in there, assuming 100% yield? Or maybe somebody's done the reaction before and it's only an 85% yield. Well, since it's only an 85% yield, how much of the stuff do I really need to put in there to get 15 grams of product? So that kind of thing. That's all Chem 101 stuff. You should be able to do that, right? It's just the excess problems and the limiting reactant problems, all that beautiful stuff. So when a chemist is doing a reaction, first thing, what's going in, what's coming out, right? That's number one. We can do that. What we're going to learn tonight is the second thing we want to know about a reaction, which is really how fast is it, right? You could have a reaction that gives you a 90% yield, right? Or a 95% yield, okay? Which is pretty good, right? Depending on what you're doing, okay? But if the reaction takes a week to come to completion, and my boss is paying me by the hour, that's maybe not the best way to go, right? I mean, time is money. Okay. Whereas maybe a reaction gives you a worse yield, maybe it's only an 85% yield, but it's done in 30 minutes. That would probably be more efficient, be better. So kinetic, how fast the reaction goes is really important. The third thing we want to, so that's what we're studying right here in this chapter, speed of reactions, right? Rate, okay, which is usually a physics thing, right? So rate, speed, right? That's usually a physics thing. So this kind of like where physics and chem start to overlap a little bit here. And then the third thing we want to know is actually our next unit, which is going to be on the second exam. It's going to be chapter 13, which is equilibrium. Next thing we want to know is, what side of the reaction does the reaction favor? Does it favor the reactant side? Do we not get a good yield? Does it favor the product side? Do we get a really good yield? And are there things we can do to influence it, to shift it to the product side, right? So that's the equilibrium unit. The equilibrium unit we do, the next chapter we do, that build like 2 chapters build off of that. So the equilibrium chapter is easily the most important chapter of all Chem 102. Not to say this one isn't important either. This chapter is kind of standalone, right? Once we do the kinetic stuff here in this unit tonight and Wednesday night, it doesn't really come back. Okay, but the equilibrium stuff that we do starting next Monday, that keeps coming back and coming back and coming back really for the rest of the class. So anyway, just a little bit of looking ahead, right? Looking ahead. Okay, cool. Kinetics. So we chemists describe reactions that happen on their own. We describe them as being spontaneous. So spontaneity is the term we use to say whether or not a reaction will occur or not. So a reaction that would not occur, like if I mix A and B together and they just sit there and they don't react, okay, that would be a non-spontaneous reaction. So spontaneity is the term we have for whether or not a reaction is going to happen. And that's really the next chapter, right? That we can kind of talk about what side's favored, what side's not. This chapter, kinetics, is all about how fast a reaction is going to happen. And in order to study how fast a reaction is going to happen, it has to be spontaneous. So we can't study how fast a reaction is going to be if it's non-spontaneous, if it doesn't happen, right? We can only study reactions that happen, that are spontaneous. Okay. You probably got a little bit of this chapter in high school with the reaction coordinate diagrams that we're eventually going to draw. And we talk about all that stuff. So I'm going to come back to the diamonds thing a little bit later. I want to get right into rates. Okay. So rate. What is rate? Rate is a change in something over a change in time. And you can see in our formulas here, we're using our Greek letter for change, which is the capital delta. You're probably familiar with that from math class, right? When you find the slope, it's the change in y over the change in x, right? Okay, so that's change. In physics, it could be change in distance over time, right? That's speed. It could be change in velocity over time. That's acceleration. But in chemistry, it's really change in concentration over time. So if you look here, these brackets are chemists' abbreviation for molarity. So when you see this, this stands for change in the reactant concentration, the molarity of the reactant over the change in time. And this bottom one is change in product concentration over time. So the first thing I want you to notice is the rate of a reactant is always the rate of a reactant's change in concentration is always going to come out negative. So that's why I emphasize this by putting a negative sign there. If you measure the change in a reactant's concentration, you're going to end up with a negative. We're going to talk about why in a second. Hang in there. And notice that the product doesn't have that negative sign there. If you measure the change in product concentration over time, you're always going to end up with a positive value. Let's talk about why that is. Pretty easy to understand. Say I have a reaction of A plus B goes to C plus D. If I, and let's say these are all gases, right? Because that's easy to understand. Okay, if I pump in a whole bunch of A's and B's into a flask and I seal it up, well, what's going to happen? We're going to start out with all reactants and no products. But then A's and B's are going to start smacking into each other. A, B, they smack into each other. And they're going to start to turn into C and D, right? We're going to make our products C and D. And then these A's and B's smack into each other. And we're going to get a C and a D. And you can see what's happening here. If we measure the rate of this reaction by the change in concentration of a reactant versus time, what's happening to the reactants? Well, the reactants are going to be consumed in the reaction, and the concentration of the reactants is going to decrease. Change is always final. Oops, this mouse. Change is always final minus initial. So my concentration after 30 minutes, my final is going to be less for a reactant than what I started with at the beginning, the initial. So you can see if my final number is always smaller than my initial number, we'll get a negative value. So that's why if you measure the change in concentration of a reactant, okay, you're going to end up with a negative value because as the reaction progresses, you're losing reactants. So there's going to be less of it in there. Final minus initial, smaller number minus a bigger number is always going to give you a negative value. Product concentration is going to be the exact opposite, though. If I can monitor the amount of product in here, well, what's happening as the reaction progresses, we're making product. So my final value after 30 minutes or an hour or 2 hours is going to be bigger than what I started with. Okay, so we're always going to have a positive value for product. So that's the first thing that tends to trip people up, right? Why is there a negative? Why are reaction rates, when measured in terms of reactant concentrations, why do they come out negative, and why do products come out positive? Hopefully, you got an understanding for that. Cool. So the next thing I want you to understand about the rates of reactants and products in chemical reactions is that they are all related by the coefficients from the balanced chemical equation. So these coefficients are really important. And what we can do is they're going to allow us to compare how fast things are being consumed or created within a chemical reaction. For example, how will the rate of the iodide consumption compare to the hydrogen peroxide consumption? So how will the rate that the iodide, this reactant, gets consumed, how will that compare to the rate that the hydrogen peroxide gets consumed? And the answer is the iodide is going to go down 3 times as fast as the hydrogen peroxide. Okay, so how will the rate of consumption compare? The iodide is going to be 3 times greater. Why is that? Well, it takes 3 iodides to make a hydrogen peroxide. Okay, imagine this. Okay, and we'll hop out here to the board. Imagine you got a job for the summer, right? Working for, I don't know, Schwinn assembling tricycles, right? So you're on the assembly line, and your job all day is to take a tricycle frame. Oh, God, that's terrible. Ugh. I mean, I'm not a good artist, but you're going to take a tricycle frame. There's the seat. Okay. And you're going to take the wheels and you're going to put the wheels on that tricycle all day, every day, right? That's such a good tricycle. Don't worry about the pedals. That's somebody else's job. Okay, so this is your job. All day, every day, you're going to take tricycle wheels. You're going to put them on a tricycle frame. You're going to make a tricycle. Okay, well, it takes one frame and three wheels to make one tricycle. Okay, now imagine that you got a pile of frames at your station and a pile of wheels at your station. What's going to happen? That pile of wheels is going to go down 3 times faster than the pile of frames, right? Think about it. I got to grab 3 wheels every time I grab one frame. This pile is going to go down 3 times faster. It's the same for chemical reactions, right? Okay, think about it. I got to grab 3 iodides every time I grab a hydrogen peroxide. The amount of iodide in there is going to go down 3 times faster. So the rate of that iodide consumption is going to be 3 times greater than hydrogen peroxide. Okay. How about the H plus? How will the consumption of H plus compare to the consumption of hydrogen peroxide? Think about that. And then once you're done thinking about that one, how will the rate of the triiodide ion, that's a product, how will the rate of the triiodide production compare to the hydrogen peroxide consumption? Think about those two for a second. All right. Well, the H plus ion consumption and the hydrogen peroxide consumption, the relationship is that the H plus is going to go down twice as fast as the hydrogen peroxide, right? I need 2 H pluses for every 1 hydrogen peroxide, so it's going to go down twice as fast. How about this one? How will the rate of the, I lost my pen. How will the rate of the triiodide production compare to the hydrogen peroxide? Well, the answer is they are going to be the same, just with an opposite sign, okay? They both have the same coefficient, a 1 and a 1. But the rate for the triiodide, since the triiodide is increasing, that's going to be positive, and the rate for the hydrogen peroxide is going to be negative. So whatever it is, 5 molar per second, 0.5 molar per second. For the triiodide, it's going to be positive 0.5 molar per second, and for the hydrogen peroxide, it's going to be negative 0.5 molar per second. Okay, why is that? Well, for every 1 hydrogen peroxide that goes in, I get 1 triiodide out. So they're going to have the exact same rate, just opposite sign, right? Because one's decreasing, the other one's increasing. So hopefully you see that, no matter what, if you have a balanced chemical equation, you can compare the rates of components within a reaction. So you would, the rate of water production is going to be twice as fast as the rate of the triiodide production because it's got a coefficient of 2. So hopefully that's making sense to you. Now let's put some numbers with it, right? So let's work through this. So here we have a decomposition reaction, right? Here we have a decomposition reaction. Let's take a look here. So we're starting here with only NO2. So 0.0300 moles of NO2. And after 50 seconds, there's 0.0237 moles of NO2. So what's happened? Well, what has happened is exactly what we would expect to happen. The NO2 has gone down, it's decreased. So we lost some NO2, right? And that's what should happen to a reactant. Okay, we started with no product in here. And what I want to do is I want to predict the amount of products that would be in here. So let's first do this. Let's figure out how many moles of NO2 we lost in that first 50 seconds. So if we subtract, right, 0.03 minus 0.0237, we lost, and I'm going to type this out because, man, when I write it with the mouse, it looks so bad. We consumed 0.0063 moles of NO2, right? That's what was consumed. And now what we can do is we can figure out how many moles of NO2 must have been produced in that time frame and how many moles of O2 must have been produced. How can we do that? Well, the NO2 and the NO have the same coefficient. They get the same coefficient, right? 2 and 2. Okay? So what that means is that for every 2 NO2s I use up, I get 2 NOs back. So they should have the same rates, right? Which means if I'm using up 0.0063 moles of NO2 in the first 50 seconds, then I should have made 0.0063 moles of NO2 in that same time interval. So this would be 0.0063 moles that should have been created of the NO, right? That's how much NO should have made. Now, how much O2 would be made then? Well, it's going to be half of that, right? Okay, we only get 1 O2 for every 2 NOs, right? Or we only get 1 O2 for every 2 NO2s that are consumed. So if we consume 0.0063, moles of NO2. If we divide that by 2, then that's oops, I divided by 3. Then that's 0.0032, right, with 2 sig figs. So we would only make 0.0032 moles of the O2. So hopefully that's making sense. These are not rates yet, by the way, because rates have to be molarity per time, right? But we're just starting to see how we can use these coefficients to compare the things in a chemical reaction. Let's do one for real now. All right. So here's some data that has been tracked, okay? And what we have here is we have really the same first 2 rows that we just did, right? We just solved for these. We predicted the amounts of that, and I put 3 sig figs on there. It's fine. I guess that actually does go out. That's fine. So if we take a look here, I just added some more cells, right? So here's what happens after 100 seconds. Here are the values after 150 seconds. Here are the values after 200 seconds. What I actually want to do is I actually want to calculate some rates. Okay. Now, rate is the change in the concentration of the thing versus the change in time. And concentration, folks, is molarity. And molarity is moles per liter, right? It is an amount per volume. So before we can calculate a rate, we have to turn these values into concentrations. Okay, so how do we do that? Well, we have the moles, and these are all gases. We just need to know the volume of the container. So I'm telling you, it's a 3-liter container. So the first thing we'd have to do before we calculate any rates, and the first thing we're going to do is we're going to calculate the rate of NO2 consumption after 50 seconds, is we need to turn these into concentrations. So we're looking at the NO2. We need to divide all of these values. We need to divide these 2 values by 3 liters. So these needed to be divided by 3.0 liters to turn that into a concentration, and that needs to be divided by 3.0 liters to turn it into a concentration. So let's do that. So 0.03 divided by 3. This is really 0.010 molar. And now let's do that for the 50 seconds. Whoops. So 0.0237 divided by the same 3-liter flask. This is really 0.0079 molar. So now we have these in concentrations. So now we can calculate the rate of the NO2 consumption after 50 seconds. I want to do the first 50 seconds. So we have T equals 0 and T equals 50. So I want to compare those rates. So here we go. The rate is equal to the change in concentration, which is final minus initial. So we're going to take the final concentration at 50 seconds, 0.0079, and we're going to subtract the starting concentration at T equals 0, 0.010. And these are molar. We'll throw a unit on there. And then we need to divide by the change in time. How much time has elapsed? Well, 50 seconds have elapsed. So we're going to divide by 50 seconds. And if we do that, and be careful of order of operations when you put this in your calculator, you got to use parentheses or you got to subtract before you got to subtract and hit enter before you divide by that 50 seconds, right? So we're punching this in our calculator, 0.0079 molar minus 0.010 molar. I hit enter, but you could use parentheses and then divide that by 50. What we get for the rate of this reaction is negative. Shouldn't be surprising. We're looking at a reactant here, so we should get a negative concentration. You should get negative 4.2 times 10 to the negative fifth, and the units are going to be molar per second, which is what we should always get for a rate. Your units for rates should be molar per second. So over the first 50 seconds, we can see how fast this reaction was going. Over the first 50 seconds, the NO2 was going down by 4.2 times 10 to the negative fifth molar per second. So that means on average, oh, that blue does not show up very well, does it? Let's go back. On average, the amount of NO2 in that flask was going down by 4.2 times 10 to the negative fifth moles per liter every second. Okay, so that's what we were able to get. And now what I want to do is I want to do the same thing, but I want to calculate that change from 100 to 150. But before we do that, I want to make a prediction. Okay, I want you to make a prediction. I'm not going to tell you the answer because we'll talk about why it comes out the way it does here in a moment. But do you think that the rate for the reaction is going to stay the same? Okay, later on in the reaction, do you think it's going to increase, get faster later on in the reaction, or do you think it's going to decrease? Do you think the reaction is going to slow down over time? So what do you think? Do you think it's going to stay the same? Do you think it's going to speed up? Or do you think it's going to slow down as more and more time goes on as the reaction progresses? So think about that for a second. Make a prediction. Worst thing you can do is be wrong. Now what I want to do is I want to actually calculate it, and we're going to compare. So I want to do from 100 to 150 seconds. So the first thing we have to do is we once again have to divide both of those values by 3.0 liters. So we got to divide by the volume, turn these into concentrations. Oops. So let's do that. 0.0195 divided by 3. That's going to be, and I'm going to switch to red because that blue is just not showing up. That's going to be 0.0065 molar, right? And at 150 seconds, oops, I shouldn't have clicked that yet. We got 0.0165 divided by 3. That's going to be 0.0055 molar. Excellent. And now what I want to do is I want to calculate the rate. So I want to do the concentration at 150 seconds minus the concentration at 100 seconds, and then divided by that same 50 seconds, because the change in time from 100 to 150 is 50 seconds. So I want to see what our speed is here. So that's going to be rate equals the 0.0055 minus 0.0065. And that's all molar, right? So molar, and then divided by 50 seconds. So let's punch that in. Again, be careful of order of operations. And we get with 2 sig figs, negative 2.0 times 10 to the negative fifth molar per second. So the first thing you should notice is that it did not stay the same. At the beginning, the reaction, the NO2 was going down at a rate of 4.2 times 10 to the negative fifth. And now, later on in the reaction, the NO2 is going down by 2.0 times 10 to the negative fifth, because that's really what the negative means. It means the concentration is decreasing, right? Okay, so what has happened? Did not stay the same. What happened is actually the reaction has slowed down. And this should make sense. All reactions are going to be the fastest they're ever going to be at the very beginning, and then they're going to slow down. And we'll talk about why. So what you should make a note of here is the reaction is slowing down as it's going. Okay, as it's going. We're going to talk about these other rates here in a second. Okay, but I want to talk about why the reaction is slowing. Actually, I tell you what, let's do these other reactions while I still have it on the screen. Then we'll talk about why the reaction is slowing down. Now that we know the rate for the NO2 consumption between 0 and 50 seconds and between 100 and 150 seconds, we can actually calculate the rate of the NO production and the O2 production over the same time interval. So the rate of the NO production, because the NO2 and the NO have the same coefficient, is that if the NO2 is going down by 4.2 times 10 to the negative fifth, then over the same time interval, because they have the same coefficient, this would be going up, positive sign, by 4.2 times 10 to the negative fifth molar per second, right? So again, the coefficients of the balanced chemical equation allow you to compare them, right? Okay, so if the NO2 is going down by that rate, then the NO is going to be going up by that same rate. The O2 would be going up by half of that rate, right? So if we divide that in half, it's going to be being produced at a rate of 2.1 times 10 to the negative fifth molar per second. Oops. And then we can do the same thing for this 100 to 150 second time interval, right? So from 100 to 150 seconds, the reaction is slowed down. We're only losing NO2 at a rate of 2 times 10 to the negative fifth molar per second. So what would the NO concentration, or what would the NO rate of production be over that same time interval? It's going to be the same. So this would be a positive 2.0 times 10 to the negative fifth molar per second. And then because the O2 has a ratio of 1 to 2, it's half of that, then the O2 would have a rate of production of half of that, 1.0 times 10 to the negative fifth molar per second. So, yeah, what's up, Angel?
So will the rate of consumption always equal the rate of reaction? Essentially, how much is being consumed is how much is going to be produced on the other side of the equation?
Only if they have the same coefficient, right? So
Okay.
the rate of the NO2 consumption is the same as the rate of the NO production because they have the same coefficient.
But the
But the rate
oxygen would be half.
the rate of the NO2 consumption is going to be twice as fast as the rate of the O2 production, or the rate of the O2 production would be half of the rate of the NO2 consumption.
Got
So
it.
no, they're only going to be the same. The rate of consumption and production will only be the same if the two things have the same coefficient.
The same number of moles.
What the coefficient of the balanced chemical equation tells you is the number of molar equivalents that are
Hmm.
going in, needed to go in and needed to come out. So if they have the same coefficient out front, same number of molar equivalents, then the rate of consumption and production will be opposites, right? One's negative, one's positive, because they have the same number of molar equivalents. Just one's going down, one's going up.
Got it. Thank you.
Yeah. So hopefully you can see how we can, number one, calculate rates. Okay, we need concentrations. So if you don't, sometimes you'll just be given molarities. Usually you'll just be given molarities. Here, we were given moles and the volume of the flask, so we had to calculate them. But a lot of times you'll just be told the molarity straight up. So we had an extra little step here. We had to divide by the volume of the container. Okay, if it was aqueous, you divide by the volume of the solution, right? But this is a gas, so we divided by the volume of the container. Gases and aqueous things are the only things that can have concentrations anyway. So we turn these into concentrations. Once you have the concentrations, you calculate the rates by doing the change in concentration over the change in time. And then hopefully you ever see that once we knew a set of rates, we could get the rates for everything else in the reaction because they're all related by the coefficients.